we solve an example of signal space concept. Suppose we are given S1 of t and S2 of t, the set of two signals S1 of t and S2 of t is given, and these are non-orthogonal signal set. If you try to find out the dot product, you will not get 0. So this set is a set of non-orthogonal signals S1 of t and S2 of t. And at the same time, we are also provided with the set of these basis function psi1 of t and psi2 of t, and we have to verify. Let me write it specifically. First of all, verify that that these are S1 of t and S2 of t, S1 of t and S2 of t forms a set of non-orthogonal waveforms, right? So we would verify that these two forms a set of non-orthogonal waveforms. Secondly, the next target would be to verify that the set of basis functions forms orthonormal this set forms orthonormal basis functions set. That verify that this is a set of let me write it this way. Verify that this is a set of orthonormal basis functions. This is a set that this is a set of orthonormal basis function. So let me erase this orthonormal basis. It's a set of orthonormal basis functions, right? Then and our third target would be to represent S1 of t and S2 of t as a linear combination, of psi1 of t and psi2 of t, right? So we will show these three. We have to show these three parts. So let me start the first one. Initially, what we have to prove, we have to verify that this is a set of non-orthogonal waveforms. So if you observe, to verify that it's really a set of non-orthogonal waveforms, what we do, we can just try to multiply both the waveforms. So if how the multiplication takes place, let me explain it step by step. You have S1 of t, which is something like this, up to from 0 to half it is -1, and this is -3. From half to 1 it is -3. And we have another waveform which is S2 of t, and if you observe S2 of t, this is 2, this is 2 from 0 to half, and this is +2 from 0 to half, and 0 otherwise. So we need to multiply these two. So if I want to multiply these two waveforms, keep in mind we do multiplication, and I'll draw the result of this multiplication here, right? And then we'll do it mathematically. Let's try to find out first graphically. So let me draw it like this. So if you see graphically, S1 of t is 1 from 0 to half, -1, sorry, it's -1 from 0 to half, right? And if you observe your S2 of t, so it is 2 throughout, 2 from 0 to half. So if you multiply S1 of t and S2 of t, that is -1 with +2 in this duration, what would you get? You would get -2, right? So we get -2. So I would draw, I would like to draw here this -2. So let me extend this line a little bit. Let me extend it, and I would draw minus. I would like to draw -2. Let me choose a different color, green color. I would draw it with a green color. So -1 multiplied by +2 in from 0 to half. 0 to half would give me -2. So this is -2. Now in the next half, if you observe your signal in the next half, so this is -3, right? From S1 of t is -3, and if we observe here, this one is 0. This one is 0 in this period. So for the next period, we are getting nothing. You will get 0. So for the next half, we would get 0, because -3 multiplied by this 0 is 0. So our signal is actually this one now. Our signal is this one. This is our signal, S1 of t and S2 of t. So this is the product. Now what we, for verification of the first part, we had to verify that this is a set of non-orthogonal waveforms. So for verification, what we actually do, we try to find out the dot product of S1 of t and S2 of t, and we integrate it from -infinity to +infinity. If this dot product is 0, then the signals are orthogonal, otherwise not. Now we already found this product. Now this is the product actually. We have this signal over here. So this is the product, and we have to integrate it from -infinity to +infinity. So it means we have to integrate this waveform, and the limit, because it's a definite integral, so the limits would be from 0 to half only, because this signal exists only from 0 to half, and up to 1. If you observe the signal, this product, it is 0 later on. So from I'll change the limits from 0 to half. The product is S1 of t. S1 of t is -1 here, right? S1 of t is -1, and S2 of t is +2 in this duration dt. and if you integrate it, you would get minus 2 in this integration. If you solve this integral, you will get minus 2. So the product from 0 to half, this is valid for time duration 0 to half. So the product is minus 2, which is not equal to 0, hence it is not equal to 0, hence this is a set of non-orthogonal waveforms. Hence, let me specifically write it here. Hence it S1 of t and S2 of t are non-orthogonal, right? Non-orthogonal. So these two waveforms are non-orthogonal. Now in the next step, what we have to verify? We have to verify that. Let me go back to see the statement. What we have to verify in the next slide. We have to verify that psi 1 and psi 2 forms the set of orthonormal basis function, right? In the next step, we have to verify that psi 1 and psi 2 is a set of orthonormal basis functions. So let me again, we can for this purpose to verify that it is a set of orthonormal basis functions, what actually we have to do, we have to two properties, as we mentioned, as I mentioned earlier in my lecture, that for orthonormal basis functions, you have to verify that psi 1 of t, the dot product of these two waveforms, psi 1 of t and psi 2 of t, this should be 0, and the energies of these signals, if you find the energies of psi 1 and the energy of psi 2, the energies should be equal to unity, then they form orthonormal basis functions. So we will try to for the solution of the second part, we need to verify these two properties, right? So let's try to verify it. Psi 1 of t and psi 2 of t. Now you can let me draw the psi 1 of t and psi 2 of t here, and find this dot product, or I hope that you will be able to draw it right now, but let me do it mathematically first. So psi 1 of t and psi 2, the dot product of psi 1 of t and psi 2 of t. So if you observe these signals, this is psi 1 of t and psi 2 of t, and we have to find this product. Now how the signals looks like, if you observe your signals, psi 1 of t, so it is something like this. So it's plus 1 and minus 1, and this is from 0 to half and half to 1. This is psi 1 of t, right? This is psi 1 of t, and similarly we have psi 2 of t, and if you observe psi 2 of t, it is throughout 1, from up to 1, from 0 to 1 it is, this is my psi 2 of t, so it is plus 1 from 0 to 1. Now we can see that our integral, now how our integral can be solved from 0 to half and half to 1. So we can split this whole integral, we can split this integral in two sub-integrals from 0 to half psi 1 of t multiplied by psi 2 of t dt plus the same product from half to 1, the same product, psi 1 of t, psi 2 of t, and dt. So we need, this is from 0 to 1. So let me solve this example and we complete it. So we can say it's equal to 0 to half. Psi 1 in this range is, if you observe it from the figure, psi 1 of t is 1 from 0 to half, and psi 2 of t is also 1, 0 to half dt, and if the second integral half to 1, psi 1 of t is minus 1, it is minus 1, and from half to this one is throughout 1, right? So throughout 1. So we can see that psi 1 of t from 0 to half, psi 1 of t is 1 and psi 2 of t is also 1, right? And from half to 1, psi 1 of t is minus 1 and psi 2 of t is 1, right? This is taken from these figures. You can see from these two figures. Now if you solve this one, what do you get? What do you get? You get half here, right? You will get half from this integral and minus 1. So you will get, if you solve it, you will get minus half from this integral. And if you add half plus half, it is 0. Hence psi 1 and psi 2 are orthogonal signals. So the first property is fulfilled. Now we can say that psi 1 and psi 2 are orthogonal. Hence we can write here, hence psi 1, the dot product is 0, therefore psi 1 and psi 2 are orthogonal signals. Now to be orthonormal, we need to verify that their energies is also equal to unity. So to find the energies, let me find the energy of psi 1. Energy of psi 1 is the square of this signal, integral of the square of this signal. So from the, by definition it is this one. The signal exists only between 0 to 1. So from 0 we can again split it into two, from 0 to half. From 0 to half our signal is unity, right? So square of, we can say square of unity, and from half to 1 again it is minus 1 square, right? Square of the signal, we have to integrate square of the signal. So if you see these in the diagram, you can verify that from 0 to half, psi 1 of t is plus 1, and from half to 1 it is minus 1, as shown in this figure, right? As shown in this figure. So we already have, this is actually, I am taking this integral from here now. So we can go further to solve this integral, and if I solve it here, if I let me solve it here. So I have 1 square. If I integrate it, 1 square is unity, so if I integrate it, I'll get half here from this integral. Similarly, if I use this one, I'll get half from that, and we are, sorry, it's plus half now, not 0. It is unity, half plus half. Half plus half is unity. So it is unity. Now energy of this signal is unity. It's verified that energy of psi 1 is unity. Similarly, we can prove that energy of psi 2 is unity, and with these two properties are fulfilled, their energies is unity, and the signal energy is unity, and the dot product is 0. So the psi 1 and psi 2 forms orthonormal set of basis functions. Now the third part is a bit tricky, that we need to represent our signal in the form of these basis functions, or as a linear combination of these basis functions. So if you to represent it as a linear combination of psi 1 of t and psi 2 of t, what we do, actually now when psi 1 of t and psi 2 of t represent they are orthonormal basis functions. So as I discussed earlier in my lecture, that we can have this two-dimensional Euclidean space, which is a signal space, and we can represent all the signals as vectors in this form, because now psi 1 and psi 2 are just like unit vector I and unit vector j respectively. So if you observe psi 1 s1, now we need to find, if let me recall it first, if you have some signals, if you have some vector in this space, if you have a vector, let me redraw it. If you have a vector in this space, something like this, so you need to represent, you have two images, the rectangular components or the images of this vector over x-axis and y-axis. Now we have x-axis psi 1 of t, y-axis psi 2 of t. So we would like to find this signal can be represented as a linear combination of psi 1 and psi 2, but we need to find these now these components. If we know these components, we can draw this vector. Now in case of signals, we have two signals, s1 and s2. So we need to find the image of s1 over psi 1. If this is a representation of s1, then we need to find the image of s1 over psi 1. So to find the image of s1 over psi 1, what we actually do, let me write it specifically as I have given in your notes. So we need to write, we need to find these images. So we continue to find out a11, which is the image of s1 of t over psi 1 of t, and which means we need to find out this dot product, the image of s1 of t over psi 1 of t. Now as we have seen that this integral a11, we can split this integral in from 0 to half. This is our time interval where these 0 to half and half to 1. So s1 of t is minus 1 from 0 to half, and if you observe psi 1 of t, that is 1, right? That is 1, and then we have from half to 1, s1 of t is minus 3, s1 of t is minus 3, and psi 1 of t is minus 1, psi 1 of t is minus 1. So we have to find out the image. This is the image of s1 over psi 1. So if we solve this integral from here, we are getting minus 0 to half dt, and from here we would get plus 3 half to 1 dt, right? And if you go ahead to solve this further. You have minus 1 and half minus 0, and then you have plus 3 and 1 minus half, right? So this is minus half from here, and this is half, it's plus 3 over 2. So what is this? This is, just solve it, minus 1 plus 3, which is 2 over 2, and this is unit a11 is, we have a11 equal to 1, 2 over 2. Now let me see the next part. The next part is for a12. Now we have to find the image of this signal over psi 2. So let me find out that one. Our next step is to find a12. So we can find a12, which is the image of this signal S1 over psi 2, right? Just need to find these two. So again we will split it from 0 to half, and we have S1. If you observe here, S1, it is minus 1 and psi 2 is 1. Similarly, from half to 1, your S1 is minus 3 and the psi 2 of t is 1. So now we need to solve this one. If you solve this one, you have minus half from here, from this integral, right? And you will get minus 3 over 2 from there. From that integral you will get minus 3 over 2. So if you this is actually this is 2 minus 1 minus 3, which is minus 2. So yours a12 is minus 2. Now we can, now it means now we have a11 and a12, the image of signal over psi 1 and over psi 2. So if you represent your signal S of t, now you can write it as a linear combination of these two. So you can write your S1 of t as a linear combination, that is a11 times psi 1 t plus a12 times psi 2 of t, and this is actually we have a11. If we observe a11, what is our a11? The value of a11 is unity. So the value of a11 is unity, which means our S1 of t is 1 times psi 1 of t, and this is minus 2 times psi 2 of t, right? Now 1 times psi 1 of t and minus 2 times psi 2 of t is, we can write it as psi 1 of t minus 2 psi 2 of t. Now this is our S1 of t. This is our S1 of t. It's 2 times psi 2 of t. Now if you have these a11 and a12, but you can represent the vector of signal S1, which we usually we use the for the vector of a11. What we can do, we use bold, usually use a bold function, right? Then we try to find out when we try to write out this signal vector, we use the bold letters. So for we can write that, okay, our bold these signal and the coordinates can be written as this one. So we have the coordinates given by a11 and a12, which are 1 and -2. If you have these coordinates, now you can represent your signal in the signal space. So we have to psi1 of t and psi2 of t, and now your a1 is positive 1, right? This one is psi1 is positive 1, and a12 is -2, so it's -2 somewhere here, right? This somewhere here. So this is +1, this is -2, and your signal point would be here. So this is a point of 1, -2, and if you draw your signal vectors, it would be this one, position vector. This represents your signal S1. This is our signal S1. This is our signal S1. This is the vector of signal S1. Now, similarly, we can find the components of another signal S2. So if we can find all these components similar, following similar procedure. We can find it for our S. If I try to find it for second signal A21, which would be the image of S1 of t, or S2 of t, sorry, S2 of t over psi1, right? And we can find A21. So if you try this example, you have again your signal exists only from 0 to half, and S2, if you observe your S2, it is 2 from 0 to half. So it is 2 from 0 to half, and psi1 is unity in that time duration, and but actually you get 1. When you solve this integral, you will get 1. So your A21 is also 1, and if you solve it for A22, we'll solve this integral directly now from 0 to half. So signal S2 of t is 2 from 0 to half, and psi2 of t, now I have to take psi2, so psi2 of t is unity from 0 to half, and if I observe it, it is unity. So A21 and A22 are unity. So it means I can write my S2 of t, I can write S2 of t as a linear combination A11 times psi1 of t plus so not A11, it should be A21 times psi1 of t and A22 times psi2 of t, right? So we have already found these psi1 and psi2, both are unity, so we can say our S2 of t is equal to psi1 of t plus psi2 of t. Now it's very easy to observe this, very easy to we can plot it in the two-dimensional Euclidean space. This is your psi 1 of t and this is your psi 2 of t, and your signal both 1, so it would appear here, right? This is plus 1 and this is also plus 1. This is the signal point 1 and 1. So this is how you represent your signal in the two-dimensional Euclidean space. Now you can observe, if you observe it, S2 of t can be constructed by adding psi 1 of t and psi 2 of t. This is what this equation says. So if you add these two waveforms, now if you add these two waveforms, let me construct S1 first. Let me construct S1 first, because we said that our S1 of t is psi 1 of t minus 2 times psi 2 of t, right? This is what our S1 of t looks like. So if I add these two waveforms, now we already have the waveform of psi 1 and psi 2, so let me draw it here. What is psi 1? Psi 1 is 1 and minus 1, 0 to 1. This point is half. This is minus 1 and this is plus 1, right? So this is my psi 1 of t, and psi 2 of t, psi 2 of t minus 2 times psi 2 of t. So psi 2 is just 1 from 0 to 1, and if I say it's minus 2 times psi 2 of t, so minus 2 times psi 2 of t can be drawn here. This is 0 to 1 t and minus 2. This is minus 2 times, this is minus 2 times psi 2 of t. This is the waveforms for minus 2 times psi 2 of t. So if you add these two, as you can see from this expression, you are actually, what you are doing, you are adding psi 1 of t and minus, you are adding psi 1 of t and minus 2 times psi 2 of t. So this is the addition. So if you add these two waveforms, what you will get? Add from 0 to half. From 0 to half, this is 1, this is minus 2. So 1 and minus 2 from 0 to half, you will get minus 1. Minus 1. Similarly, from half to 1, this one is minus 1 and this is minus 2. So minus 1 and minus 2, you will get minus 3. And this is our signal actually. This is our signal S1 of t, which can be constructed by the addition of these two waveforms. Similarly, we can verify that our S2 of t, we can have S2 of t, we can construct our S2 of t, or we can write that our S2 of t, S2 of, now S2 of t is, if you see the equation, S2 of t is just the addition of psi 1 of t and psi 2 of t, because both the coordinates are unity. So if we add S2 of t, now again adding these two, let me, instead of drawing it again, I would use the same figures. If you use these figures of psi 1 and psi 2, as you can see, psi 1 and psi 2, or let me draw it because we have drawn 2 times psi 2. So what we have done, we have two waveforms, psi 1 and psi 2, and our psi 1 looks like this, right? From 0 to half up to 1. This is our psi 1 of t plus 1, and this is minus 1. Similarly, we have our psi 2 of t, which is unity. So in this derivation, it is plus 1. Right? This is our psi 2 of t. So if I add these two waveforms, what would I get? See, from 0 to 1, from 0 to 1, from 0 to 1, psi 1 of t is unity. From 0 to half, sorry, 0 to half. 0 to half, this is also unity. So 1 plus 1, I would get 2. And now from half to 1, it is minus 1, and here it is plus 1. So I will get 0, 0 in this derivation. And this is my, if you observe it, this is my S2 of t, which is constructed by adding these two waveforms. So I hope it is now clear to you that if you have orthonormal basis functions, you can represent non-orthogonal signals using the orthonormal basis functions.